descent to minimize the square error. So, like that. So it's a regression problem. Right. So now maybe it's a couple of interesting things that one might observe. Let's start actually the discussion with the univariate setting for simplicity. So we have a rectilinear unit, meaning we compute an affine function and take this maximum of 0 as the value of that affine function. So that's a piecewise linear function, and it has two linear pieces, 0 over identity, and so the breakpoint is going to be located at some point depending on the W and B, right? So basically, there's going to be a transition between this thing being 0 and being positive that happens at 0. So we have Wx plus B equals 0, that's the location of the breakpoint. And we can look at, what is the x that solves that? It's going to be x equal to minus b divided by w. So that's the location of the breakpoint. If we initialize multiple neurons at random, then there is going to be breakpoints located at random over the input space. So it's an example, a single ReLU initialized at random. It may look like this over a one-dimensional input. Several ReLUs may look like this. And in a shallow ReLU network, we're adding multiple such ReLUs. If we add them together, these random guys, maybe we get a curve like this. The function at initialization. And it has different kind of kinks here. And those are kind of concentrated around the positions where those breakpoints are located. And outside of there, or when there are not too many breakpoints, the function looks more or less linear or kind of piecewise linear. And so, and in fact, so you could imagine that this is going to have some kind of an impact on the solutions that you obtain for training. That there's going to be some locations of the input space that have more wiggly form than others. So we're going to see how the density of the parameters, the density that we use to initialize the parameters, induces a breakpoint density, and how that enters the solution. Okay, here is a result for an implicit bias description of gradient descent for a shallow ReLU network for univariate regression. So one-dimensional input, a single input, and so we consider a feed-forward network as given before, single input unit, hidden layer of n ReLUs, and a single output unit. We assume a standard parameterization, that's the one that I showed you. And each hidden unit will have an input weight and a bias that are initialized from a sub-Gaussian. So we have here a joint distribution of W and B. And we're going to just assume that it's sub-Gaussian and has some density. Then for any data set and sufficiently large number of hidden units, so actually, I should have presented here a different formulation of the statement. So maybe ignore this for a moment. We run full batch gradient descent with sufficiently small step size. Then we will converge to some parameter that outputs some function. So the function with the converged parameter, and that one has 0 training error. Right. So this is kind of part of the question that what happens with the optimization. You're assuming that it converges, not assuming that it converges. So there is a lot of work in that front, and in particular, you can show that gradient descent with full batch updates and some choice of the step size will actually convert to 0 training error. So that's not yet a bias. Now is the statement about the bias. So the bias will look like, to describe that, let's look at this part first. So this function that we converge to is we're gonna compare it to some other function g, and compare here the distance of those two functions. We're gonna say that it's gonna be small. The distance is 1 over square root n. We're saying the final function is close to some other function. Close in the sense that this difference is less than 1 over square root n. N is the number of hidden units. So the bigger the network, the smaller is that discrepancy. All right, and what is that function g star? That function g star is going to be given, is going to be a solution to some problem, similar to the formulation that we had before. Okay?
Is this O of n to the minus 1/2? Is this uniform over n, or is it for each fixed m, the dependence is O of n to the minus 1/2?
There is a uniform result that is relatively the same.
So that holds even for under-parameterized networks?
Oh, I see what you mean. For another parameterized net, okay, you might need to have that this is for n larger than something. It is an asymptotic. Is that what you mean?
Because then could you take just m to be much larger than n?
M being?
So m here is the number of data points, right?
Oh, yeah. Okay. Hmm.
So then could you, like if this was uniform in m, could you take m to be much larger than n? And then we have an under-parameterized network and you would still have this like bound for the kernel regime?
That's a good question. I mean, this holds outside of the training data as well. Yeah, but if you start making M.
But then you still have to fit the training data, right?
That's true. Actually, okay, we can discuss more details after, but this bound actually holds over the optimization trajectory as well. And because essentially what we're trying to say is that how well is this function being tracked by the infinite width limit, or and so for the infinite width limit, yeah, you can have a data set that is really sized with it, as long as it is finite. So that would be indicative that it should hold for different values of m. But the comparison of n and m might be a little bit more subtle than I can say. Let's get on to that. Other comments? Okay. All right. So, anyways, so we have the converse solution is close to some other function, and that other function is a solution to some problem. This is kind of analogous to the discussion of the linear model that we had before, and where we say, we have some other optimization problem that is going to capture the solution of the optimization procedure. Here, we're going to have a constraint as before, and the constraint is that we're fitting the data, and we're minimizing something. And that something that we're minimizing here is this expression. So we take here the function at initialization, theta 0, the initial parameter. We take the second derivative, and we compare that with the second derivative of our search variable here. Take the square, and integrate over the input space. So we're sort of minimizing the square of the second derivative relative to the initial function. And we have another function here, kind of a weight, that depends on the location in the input space. All right? And so, okay, I'm going to show a figure in a moment, but so if we minimize the square of the second derivative, it's as if we say we don't want to be very curvy. So we want the function to, if you had a 0 second derivative, then the function would be linear. So we're penalizing curvature somehow relative to the initial function, but the penalty depends on the location of the input space. And that location, this function zeta, is described up here. And you can think of this zeta as being a curvature penalty function depending on the input. And it is depending on sort of this integral. It depends on the probability distribution that is being used to initialize the parameters. So in a sense, you can picture that W minus Wx, this might be related to breakpoint density that we discussed before. And this is sort of related to how variable is W at the breakpoint location. So you look at the breakpoint location and you ask how much variability do we have in the values of the weights. So that's what distantiates basically the curvature. All right, so and this kind of controls how much you are penalizing the second order derivative at different locations of the input space. Okay, so here's a picture. It's just comparing the solution to the two problems. So we see here in the comparison between the solution G star to that variation of problem and the solution of the then descent optimization in the network. That would be f of theta star. And we see how this depends on the number of neurons for different optimization problems. So let's say that, so we consider a setup like this one. So for 160 neurons, the data points here are the blue dots, and we're trying to interpolate them by minimizing the square error. The orange curve is this solution to a variational problem. So it is a curve that interpolates the data point that tries to minimize the curvature penalty, that variational problem. So this is a smooth orange curve. And in teal is the solution of the optimization for a neural network if it has only 160 neurons. As you make the number of neurons bigger, you are capable of actually fitting that data better. But it's not only that you're interpolating the data better, but the curve is actually getting closer to that orange curve. And you see that for 10,000 neurons, both curves are essentially identical. So that's quite interesting. So we're actually interpolating the data, but the function that is interpolating the data is quite smooth. And what kind of smooth function is precisely the smooth function that solves that variational problem like we thought. We can plot the errors. Like if you look at these kind of figures, many of these figures for different numbers of neurons, so we can plot the error between the teal curve and the orange curve over here. And it sort of is decreasing. This is a log scale. So this line is telling us that it decreases like 1 over square root n. Yeah.
So G star is not the true data generating function, it's simply the solution to the variation problem.
That's right. Yeah. That's right. I mean, here we are just looking at one particular training data set. Those are the blue dots. And yeah, so I mean, we're not saying anything about generalizations or anything about infinite data sets, just a fixed data set. I mean, one thing or one of the consequences of this for sure is that, I mean, so making a statement about the generalization of the trained neural network is not trivial, but making a statement about the generalization error of the solution to a variational problem is easier. It's a classic problem. So there are generalization error results for interpolation with splines, so smooth functions, that one can use then to describe the generalization error of the neural network, precisely because the neural network is going to learn a function that is close to the solution of that variational problem. So, like if you had a particular data generating distribution, then you could say something about what is going to be the error based on the fact that the solution is solving this variational problem.
Is it an accident that the powers of 4 times n in this n?
In the figure? Oh, this is just the figures that are plotted here.
The numbers are just the powers of 4. Is it by accident?
Here?
160, 64, 256.
Well, we cannot plot 10,000 plots, so just make a choice of plots. It's just powers of 4.
Oh, I see.
No, but you can tell that there are a couple of numerical aspects here that one could actually take a closer look at. Because you see, for example, this teal curve, the solution of the network, is not interpolating the data really. But a network with 160 neurons is actually theoretically able to interpolate those points. So there are some other effects here that are not represented here in the figure. If you were actually to train the neural network to interpolate those data points, the error might be much higher between the orange and the teal curve, but that's not captured here in this figure. So that's maybe an interesting thing to observe. Right. Potentially, but yes.
The error as a function of the number of neurons, is that always
As a function of what?
As a function of the number of neurons. Is this always concavenated out, or are there some places where the error might slow down? Or the
This one?
yes, yeah.
If it is concave,
Is it always concave down or convex?
there is no reason to expect that it will be concave or convex. So, but essentially the statement that I made in the previous slide was that the distance between these two functions has asymptotic order 1 over square root n. And so here all that we wanted to verify is that indeed this is bounded above by, as it should be asymptotically, by 1 over square root n. So up to multiplicative constants and maybe starting from a sufficiently large n. This goes back to the question that Kara asked a little bit, like what happens if, for finite n, where n is small compared to another train data. So in reality, the statement is only asymptotic. It's going to fix the n to be on the safe side. Right, and this is just the upper bound. That this log plot would look like a straight line. The real behavior could be different, could be lower. Could be that at the beginning has some kind of front behavior and asymptotically it has this upper bound. Yeah. So, but at least these experiments and actually all the experiments that we conducted, they seem to look like this. And that's interesting because actually we had theoretically only an upper bound, but it seems to be also a pretty good upper bound. Like it's kind of a pain. Like it could also have happened that the actual error is lower, but no, it seems that that pretty much captures precisely how far you are from that solution to the functional problem. All right, so maybe we can try to understand a little bit of that curvature penalty function. So the function zeta, recall that it had this particular form, and like we can say that if you look at different, so this particular form you see it depends on the probability distribution that is used to initialize the parameters of the network. And so if you initialize the parameters, there are different standard parameter initialization procedures, for example, Gaussian or uniform in an interval, or Gaussian with a different variance. And depending on how you do that, this function is going to look different. And so these are just a couple of examples. The green curve is what you would obtain from a uniform initialization from some interval. And blue is from a Gaussian with some variance, and orange is from a Gaussian with another different variance. And for those three different initialization procedures, we are illustrating here the solution to the variational problem. So when we have a different curvature penalty function, the data is these 5 blue dots. And you can see that all of the curves interpolate this data, but they interpolate it quite differently. So the orange interpolates it kind of with a very strong peak here, and over here it is flat. So the curve that is passing through this blue dot is flat, it's linear at the dots. And here it is very pointy. And maybe that's consistent with this curvature penalty, that it peaks here at the location 0 and is close to 0 down here. On the other hand, kind of the green one is here is flat, and you see that the curvature of the green curve at this point, and this point is kind of comparable. And the blue one, well, something in between. So indeed, depending on the initialization, we're gonna more strongly penalize curvature at these points, or less strongly penalize curvature at this point. So there is going to be those compromises happening, and that is influenced directly by the probability distribution that's used to initialize the parameters. Yeah.
Are there generally other forms of this curvature penalty function?
Great question. Yes. Depends on how you initialize the parameters of the network. And in fact, we can show that you can actually create a parameter initialization distribution that will generate an arbitrary curvature penalty function. Right, so this is just a couple of examples of what this function is for different probability distributions. So you do Gaussian with some variance here for the bias and for the weights, then that zeta looks like this. If you do uniform in some, okay, this is binary, and uniform for the bias, then you get a constant. And if you get uniform on some interval, both for the weights and biases, you also get zeta being uniform on some interval. The interval that contains the training data. So then you will penalize curvature everywhere the same. In between the training data, outside of the training data, since you don't have any breakpoints and the training data points, so you will just get a linear function outside. Alright, so this is to illustrate that if you choose the variance differently, the solutions change. So, if I flip here between the two slides, one of them becomes more pointy here at 0. That is the one that has here a smaller variance. Excuse me, the smaller variance for the biases. But the error still behaves pretty much like in the first plot that I showed you. It's still 1 over square root n, and that doesn't change, even though some of the constants may change. Okay, so exploiting the initialization, this is precisely your question. So this is just showing that one can construct any curvature penalty. So like if you if you're given a function rho from R to Y non-negative with some conditions, then we can set the density of the breakpoints in such a way as to obtain, one over rho, and then make a good choice of the distribution for W, and finally end up getting that this curvature penalty essentially is proportional to this function rho. So we can create any function, any curvature penalty function by picking a corresponding distribution for the weights and biases. Right. So what this means is, well, essentially you could play around with the initialization distribution to generate or to create different types of implicit biases from the optimization procedure, either because you want to be more smooth in some locations of the input space, or because maybe you have more data points in one part of the input space than in another one, or things like that. You can also use this to play around with the generalization error. So you can formulate some of these generalization guarantees that depend on the curvature, and you can play around with this in order to optimize those bounds on the generalization error. Okay, so next, we can also think about the optimization trajectory path, not only the converged solution. This is a bit harder though. So for the converged solution, recall that, at least in the previous part, we thought that we can do first order optimality conditions, and based on that already complete bunch of stuff. That you may wonder, what is the path that you're taking between the initial point and that converged solution? What does that look like? And at the level of functions, one heuristic here, this is not very accurate, but is something like that. Let's say that you substitute the constraint optimization problem by a regularized optimization problem. So you try to optimize this functional, the curvature penalty thing, but you add, instead of having the constraint that you're interpolating the data, you add that as an additional penalty. So here we have our functional, and we have added basically the constraint, but now as a penalty, and we can balance between the two guys. So how much we emphasize one versus the other, and we can do that depending on the time step of the optimization procedure, and we can relate that with the step size and the number of iterations that we have done, and it is possible to bound the distance between this and the function that you have at a particular time step in the optimization procedure. This is being illustrated down here. So this is a low-dimensional, two-dimensional PCA of the trajectories. So we take the functions and we represent them in 2D, and we plot the trajectory that is obtained from this representation and the trajectory that is obtained from training. And so one is in red, the other one is in green. And indeed, they're close to each other. They never go too far from each other. And they converge to the same to 1. This is kind of the result that we had in the theorem. So they actually converge to the same point. But in between, we don't really know. But this seems to be a kind of a good description of that trajectory. In terms of the functions, this is what it might look like. So maybe both of them were initialized at functions that look like 0. And the red one starts moving in a particular way towards fitting some data points, and the green one as well. They are not exactly the same, but let's say that doing something similar. This is also interesting from a perspective of what is called spectral biases. The notion of a spectral bias is the idea that maybe we don't only care about what type of function we converge to, but how quickly are we converging towards some function. So it could be that, imagine we are learning, but we say, it could be that we start learning some things faster, and other things takes us longer to learn them. And in a spectral bias discussion, that's precisely what we do. We say maybe the mean value of the outputs, we fit that super fast. And then we fit super fast with the second order, Taylor expansion, and the third one, the fourth, and the higher orders maybe are fitted gradually, more slowly, and with a slower learning rate. And that's part of an analysis that is also possible. And you know, if you go and look at this picture, we can use this to understand also things in that regard. So in fact, the solution to a variational problem like this one, this is called a smoothing interpolating spline or smoothing spline, meaning that we're balancing between being smooth as possible and actually interpolating the data. And for those, you know, we can also argue therefore that maybe we start with something smooth and we then gradually start fitting higher order frequencies. So as I said, this is sometimes referred to as a spectral bias. There is a lot of more recent work capturing this from this neural tangent kernel perspective, where we basically do a spectral composition of some kernel and try to see that some of the eigenfunctions are fitted faster because we have higher eigenvalues. Comments? All right, so maybe next, just to mention that these results can be generalized to multivariate regression. So I showed you first this picture just for the univariate network, and it's interesting enough, but you know, there is also a formulation of the whole business for the case that you have more than one single input. Right, so in that case, the variational problem looks a little bit different. We don't have here the second order derivative, but something a little bit more complicated. There is a Radon transform, there is a fractional Laplacian, you know, but still there is some functional here that is being minimized subject to some constraint, the constraint being to fit the data. And the form of these objects, that depends on the activation function that we're using, that being precisely the range. The function to Radon transform is something that a couple of works have been exploring and have been pointing out, and that comes out more or less from the fact that the breakpoint for a multivariate ReLU unit is some kind of a hyperplane. There's hyperplanes that are popping up you know, for all the different orientations of the network, of the neurosat visualization. But morally, the result is similar. So we have the solution of training is close. So in the order 1 over square root n to the solution of this kind of a variational problem. Now, you know, can we think about this as a smooth function? So previously, I was saying that we're biased towards smooth functions that have a low value of the second derivative, or the square of the second derivative. Here, the intuitive interpretation is a little bit more subtle or maybe less direct, but still we can think about it as minimizing some kind of a global notion of smoothness along hyperplanes, or something like that. All right, so other generalizations are possible, for example, to other activation functions, and because a lot of these proofs, the proofs are, you know, using some, let's say, more abstract properties of the ReLU, and those abstract properties can be generalized to other activation functions. In particular, if instead of taking a ReLU, we pick some function that is a Green's function of some linear operator, that would be some differential operator, meaning that we apply that operator to the function and we get a Dirac delta. Then we can say that, so we're going to be able to describe the implicit bias for a network with that type of activation function in terms of this differential operator L. Sort of. You know, and so we can, for example, assume that under some assumptions, like homogeneity of the activation function, one obtains a result of this sort. So now we have here, you know, the functional is expressed in terms of this L. We're still subject to fitting the data, and we have a curvature penalty that is now described, but it's similar to what we had before, but we substitute here kind of the operator that is used to describe the penalty. Okay, so it's a bunch of related words. Maybe there is work describing, for example, what do functions look like in a network that has infinite width, but that has bounded norm of the weights. So in that description, there is a relationship between the type of function that you represent and the norm of the weights for an infinite width network that are given also in terms of Radon transforms. And so that's maybe an interesting line of works There has also been work on implicit biases for univariate ReLU networks that train, say, only the output layer. That has some zero initialization, so they don't account for this commutative penalty in the way that, the difference to the initial function. There are some other settings where maybe you don't have the standard parameterization, and you might end up getting an implicit bias that is not in terms of the square of the second order derivative, but maybe something else. So for example here, if you have infinite width networks with two norm weight regularization, and you can end up getting some solutions that end up being linear splines, meaning piecewise linear functions that go to the data points, as opposed to cubic splines, which would be one example of the solution that you have in this setup. So that's all quite interesting. Okay, so summary at least for this part is that we have very descent for all parameterized ReLU networks, and this is biased towards functions which have low curvature in some sense, and the parameter initialization determines the curvature penalty that is instantiated, and there are extensions of these two different settings of multivariate networks, different activation functions, and optimization trajectories. Okay, so questions? Yeah.
Could you try extending the shadow result to like perhaps non-fully connected three-layer networks, right? So if you still have like, it seems like you could sort of just connect capsonate to another layer and still retain the G understanding, and then like get a linear condition. Would that work? If you just add another layer and something like that?
Yeah, extensions to this case are very interesting, and they are not covered here. So that's still an interesting thing to look more closely into. So, I mean, some type of results are possible if you think about the description of the implicit bias in terms of the parameter. So, some kind of, for example, minimum norm solutions for the parameter. What is of interest here in this discussion is the description of that implicit bias at the level of the functions. But at the level of the functions, that's an interesting problem to look at. So what is the nature of the functions that you represent with a deep network if you have bounded norm weights? I think that's an interesting question. I'm not sure. So that definitely is less well understood than the shallow case. Maybe you could, for example, also say, okay, I'm going to fix kind of the representation of a certain layer and only train the last layer. You could do things like that. Or you could do things like, let me try to understand the activation function as being this complicated, first part of the network. So that was actually part of the also looking at this extension of the activation function. Maybe you can create or try to interpret the deep network as a rule with some kind of crazy activation, and then obtain a corresponding differential operator and express the balancing function space for that case in this way. But this is certainly something that would be interesting to see to develop in details. How much time do I have?
15 minutes.
15?
14.
14? Okay, so if there are no further questions to this, I might just tell you briefly about some other topic. Okay? Okay. Then let me just interrupt the video for a moment and switch my slides. Okay, so you had maybe mentioned tentatively about speaking about architectures. It's a lot of architectures that one can talk about, and certainly too much topics. But one particular instance that may be interesting to discuss, at least to me, is that of linear convolutional networks, because they have a setting where we can be very accurate in the description of the functions that we can represent. And you can also try to think about the optimization problem that arises there. And so, in particular, the thing that I was discussing during the coffee break with some people is that of, can you have some kind of a bias in the case of an under-parameterized network? So you may have actually a network that has many parameters in relation to the data and still is subject to constraints. And in that case, maybe you have multiple local minima in function space, and you may ask, is there maybe a bias towards some of the minima, depending on the optimization procedure, maybe the initialization, things like that. And indeed, some of those things can happen and do happen. So, what is a linear network and what is a linear convolutional network? Linear network is, you parameterize linear functions, but you write the weight matrix as a product of some other factor matrices. And for a linear convolutional network, you're just simply going to say that, so we have a product of matrices, that's just a linear network, and in the convolutional case, those factor matrices are going to be convolutional. Convolutional matrices means they are subject to some linear constraints. So certain entries of the matrix are 0, and some of these weights are repeated across rows of the matrix. Right, and it's interesting because this already imposes some constraints on the functions, but also gives rise to interesting constraints in the, well, it gives rise to interesting constraints as a matter of fact. If you're just multiplying unconstrained matrices together, the worst thing that can happen is that the end-to-end matrix is going to be low rank. But if you subject these matrices to some linear constraints like here, the product might end up being some matrix with some other types of constraints. So let me tell you a little bit about the geometry of that set of functions that you may obtain, maybe a little bit about the optimization for that. It's not a lot of time, so I'm not going to spend too much time in the detail. But so you may ask, for example, when are you going to be able to capture all the matrices that you could at a naive level imagine that you could get, but expressed in this factorized manner? That's something that can be characterized. It's like so, like the factor matrices have a certain property. It is possible to actually show that you're going to be able to represent all of the matrices. But otherwise, there are going to be some constraints. So a matrix is actually containing this function class of the linear convolutional networks if and only if these filter sizes, the factor matrices, they have some filter size. And if that filter size has some properties, only then you're going to be able to represent that matrix. And actually, the set of the representable matrices end-to-end is going to be a semi-algebraic set, meaning that it is cut out from an ambient space by some polynomial inequalities and polynomial equations. Give you a picture of what that might look like, and just maybe to highlight the fact that you may be over-parameterized and yet subject to constraints. In this case, we may have, this is an example of a network with 2 layers, and for this network with 2 layers, and inputs of size, in this case, 3-dimensional inputs. So if you're going to represent a linear function on 3 inputs, it's going to be represented by a vector with 3 components. And so I'm plotting here what are the vectors that you can end up getting for a linear convolutional network with 2 layers. So the set that you can express is actually 3-dimensional, but it is subject to inequalities. So this surface here are the inequalities that are satisfied for the representable vectors. The vectors that you can represent are sitting on this side of the surface, but the surface is kind of the boundary of the set of representable vectors. And that's interesting because, yes, you have sufficiently many degrees of freedom. You have more parameters than data points, but you are still subject to constraints. And so if you were to run optimization in here, it may be that over this region, maybe there are multiple solutions in terms of parameters. And over here, maybe you don't have 0 error, but the closest point that you can get also can be represented by several parameters. And maybe actually there are several local minima that are kind of the same type of error. Let's say this surface is supposed to be something like a cone. So that's the boundary of the model. And you have some data points, some data set, and you try to find the closest point in your model to fit that. It could be that there are several of them. And the one that you're gonna pick is gonna depend on your initialization procedure. So that's of interest. So there's a couple of analyses that is possible to make in here. Maybe I'm just gonna skip and go to some experiment. Maybe I can show you this picture before going there. This is another example for another one of these networks, and it's showing something that is actually interesting, and that is the notion that, so again, this is illustrating the set of functions that you can represent, and there is a boundary here, described by some surface, and over here you can represent everything, so this linear maps you can represent. So if you think now of a target function that you want to, or a target data set that you want to fit with this model, there are going to be different things that can happen depending on what that data is. So if the data is sitting over here, the closest point is going to be sitting over here at this surface. But if your data is over here, then the closest point is going to be sitting on this line. That's funny because it means that over here, like usually there's going to be, as you change the data a little bit, you're going to get a different solution. But over here, if you change the data a little bit, you still get the same solution. That's kind of interesting. Sometimes people talk about Voronoi cells for some sets. So you can imagine that over here, the Voronoi cells are one-dimensional, and over here, the Voronoi cells are two-dimensional. And what that means is that you have really a very strong bias that is being induced. So because you modify the data quite a bit, and you can't denoise it because you're mapping it to something dimensional. Over here, if you have noise, it still is going to be reflected in your solution. So that's kind of interesting. That you can have that sort of behavior in a way that depends on what is the type of data that you're using. So for some data, you remain sensitive to the noise. For some other data, you cancel out that noise. So these are things that can be, kind of explored. And in this particular case of linear convolutional networks, described quite explicitly. So that's interesting. For the optimization problem, so there are several questions that you may ask. But in particular, if you have a neural network, you may ask, are the critical points in parameter space related to critical points in the space of functions? So what is the relationship? Could it be that the local minimum parameter space corresponds to a local minimum in the function space? So why am I saying that? Is because the parameterization could introduce some local minima that are spurious or are not really part of your set of functions, but are introduced just in virtue of the parameterization not being linear. And so there are two types of directions of interest. One is the notion that a critical parameter, so if you think of the loss in function space, then that's going to be also a critical point of the loss of the parameters. But the other way around is not so obvious. If you have a critical point, critical parameter, does that correspond to a function that itself is somehow a critical point? And in the case of these convolutional neural networks, linear convolutional networks, you can actually establish some relationship between these two things. And there are a couple of interesting things that happen. So here, this experiment is showing different types of target data sets. And these data sets fall in different chambers, as I was trying to explain, which have different behaviors. And here we track, what is the nature of the solution depending on what that target was. And we see that for certain types of targets that have some characteristics, there are multiple solutions that may arise. And for some others, there is just a single solution. So it's a kind of a splitting of the space of parameters depending on the target function that you are trying to represent. And this arises entirely due to the parameterization of the model, because in fact, if I'm not mistaken, in this experiment, both these classes, they represent the same functions, but they represent it with different parameterizations. So one parameterization here are networks that have 2 layers, and here are networks with 3 layers. In the case of networks with 3 layers, there is kind of a more fine-grained decomposition of things that's going on, and there are some critical points that you may end up landing to upon optimization that did not happen for the other network. So this could be another type of bias, if you like, that is induced by the parameterization. We have the same class of functions, but we parameterize it differently. And now when we run optimization for the same types of targets, we get different solutions. These are just different types of critical points in a deeper network representation of the problem. I think this is interesting because, yeah, so it is, you can also think about this as a type of a bias that is induced by the parameterization, just the fact that you're going to have different critical points because of the form in which you are writing the optimization problem or the parameterization. All right, so I mean, there's too much detail, much more detail than I can tell you about here, but maybe I'm just gonna stop here. Yeah. All right. I'm gonna stop here. Let me pick one fun picture. If I, maybe do I have the fun picture here? Oh no, I didn't add it. Okay, so I'm gonna stop here. Thanks for your attention.
Sorry, I had a quick question about the surfaces you showed earlier.
Yeah.
Could you talk a little bit more about what factor? So how do we create that surface again? What was
Okay, that's not super trivial, but essentially, I mentioned the set of functions that you can represent happens to be semi-algebraic. So it is described as the solution set to some polynomial equations and polynomial inequalities. This is the polynomial inequality. This is the polynomial inequality plotted as a hypersurface in some space. There are some approaches to obtain this systematically. They tend to be computationally expensive. In some small examples, we can construct them essentially by hand, by evaluating essentially the Jacobian of the parameterization map and seeing where it vanishes, and setting that as an equation. And if you try to write down what the solution set for that equation, what is the equation that corresponds to? That could be a polynomial, or you can try to write down.
And so does the parameter, so like if we, parameterize our function class differently, does this surface changes based on that?
Right. What is funny is that I showed you these two examples. They are the same function space, right? But so the surface in this case is the upper part in here. So the function space is everything that is down here. The boundary is actually just this part. But in one case, you get another structure inside that also produces some other splitting of the lost surface in parameter space. Something like that. The question was what? Just
Yeah, I mean, just thinking about this a little bit more.
yeah, it's a good point. I mean, okay, one of the things, maybe just to provide a little bit more intuition of what happened here, is that for linear convolutional networks, they have the nice property that you can interpret them as polynomial multiplication. And once you start thinking about polynomial multiplication, you can establish conditions for describing these functions in terms of polynomial factorization. Polynomial factorization essentially means that you're looking for the roots of a polynomial. And the roots of a polynomial, they can be discussed in terms of these real root multiplicity patterns or discriminant hypersurfaces, and in some cases they are characterized. And some of the surfaces that I ended up plotting here are actually discriminant hypersurfaces for polynomials of a certain degree. But these are for the cases that they are cataloged. Generally speaking, we know that a discriminant hypersurface exists, but we don't know what it is. So, kind of in full generality, we don't really know what these surfaces are. Even in theory, we sort of have an idea.
But every architecture has a surface like this.
Yes, every architecture has a hypersurface. And I guess part of the thing that I was trying to say is that this is sort of splitting maybe, I can't say, you can imagine this is the space of functions that you can potentially represent. And this is kind of partitioning that space. So some part of it is the function that you can express with the network, but also there is another partitioning that may or may not arise through the parameterization. So like points in this surface can arise as critical points of the optimization in parameter space. But
You isolate those.
we have isolated those differences in this case of linear convolutional networks.
But generally, it's Generally, it's difficult because, yeah.
Outside of linear convolutional networks, I think this is a really interesting work program that is not done yet. So. Yeah, but maybe hopefully this is kind of understandable, but this is sort of saying that if you optimizing parameters, you optimize the parameter, you may hit a critical point. And we have a description of what that critical point means in function space. So it could be, let's say, these are going to be functions that are sitting in the boundary between these kind of hypersurfaces. And these are analogous to saying these are going to be smooth functions of some nature. And those are the critical points that you may encounter in parameter space. Yes?
Are all setups for LCMs equally expressive?
No, what do you mean? No.
If some choice of stride is less expressive than another. or
Oh
some
yeah, that's a great point. I showed you only figures here for stride 1. That if you have stride bigger than 1, in particular, you will not be able to. There are only inequality constraints. For stride bigger than 1, you have also equality constraint. So you don't get a full dimensional set of convolutional functions, but only a lower dimensional set of convolutional functions. As soon as you have bigger strides. And even if you have only stride 1, you may be subject to those inequality constraints. That's the kind of this theorem that I didn't manage to show entirely, but yeah, that characterizes the cases when you actually can represent everything. I think is it should be given in one of these theorems. Oh yeah, so the architecture is fitting if and only if this condition is met. This condition means that the number of even filters is at most 1. Yeah? So filters of size at most of even filter size, if you have more than 1 filter of even size, you are not going to be able to represent every linear convolution. So the characterization is quite complete here in this theorem.